All right, so this is the last problem in the Unit 6 packet. So we've got steam enters an insulated turbine at 10 megapascals, 480 degrees Celsius, and zero point 0.3 meters cubed per minute. You'll notice that this differs a little bit from the wording of the packet. So I added the temperature on there because that was some missing information there. It leaves at 10 kilopascals with a quality of 90%, and we want to know the power output, W dot, in kilowatts, and the isentropic efficiency of the turbine. So I've went ahead and put our given or find or assume on there. So typical assumptions for a turbine, steady state, Q dots equal to 0, and changes in kinetic and potential energy are negligible. And the way that I think am going to solve it is I'm going to kind of keep a graph over here or a table of all my properties. So I've got a couple of different properties. State 1, self-explanatory. State 2 is defined by the pressure and the quality that they've given us. So those operating conditions that they've given us. State 2s I'll need to keep track of because I've got to find the isentropic efficiency. And keep in mind that state 2s, the isentropic efficiency, it's defined between two given pressures. So you'll notice that P2 and P2s, they're both 0.1 bar. And then the only other thing that I've put on there about state 2s is that the entropy at 1 and state 2s are exactly the same. So, all right, so first things first, apply our conservation of mass. Not too exciting there. Just says that the mass m dot 1 and m dot 2 were equal to one another, and we just call that m dot. And then our conservation of energy for an open system, dE dt equals Q dot minus W dot plus the sum of a whole bunch of stuff going in minus the sum of a whole bunch of stuff going out. It's steady state, the dE dt goes away, Q dot goes away, changes in kinetic and potential energy go away. And so all we're left with is the W dot and the sum of the M dot H's coming in minus the sum of the M dot H's going out. And since M dot 1 and M dot 2 are equal to one another, I've just put that as M dot. So I do need to go ahead and calculate what that m dot is, and the information that I've got from the problem statement that tells me the rate at which things are happening is the volumetric flow rate. So I use the volumetric flow rate divided by the specific volume at state 1 to get the mass flow rate at state 1, or just the mass flow rate at state 1 or state 2. But we're using the volumetric flow rates and the properties defined at state 1 to figure out that m dot. So for this, I need the specific volume at 1, I need the enthalpy at 1, and the enthalpy at 2. So state 1, that's defined by the temperature and the pressure. If you look on the saturated tables, you'll see that it's superheated, and so you could see that in the table on the upper right-hand corner. So I've labeled that it's superheated. I've pulled the specific volume off of table A4, as well as the enthalpy, and I think I'll probably need the entropy as well, so I've pulled that as well. And then I've also kind of updated my table at state 2s to reflect that S1 and S2s are equal to one another. And so if I plug in, and the H2, remember they gave me a quality in the problem statement. So state 2 is defined at 0.1 bar with a quality of 0.9, and it's saturated, of course. So I do need to use that quality to calculate what H2 is. If I wanted to, I could pull other property data as well pretty easily. So you could see I've got some numbers sort of in gray on that table. So the temperature at state 2 is the saturation temperature at 0.1 bar. The specific volume would be calculated with the quality, just like we did with the enthalpy. Same thing with the entropy if I needed it. I don't think I need it for this problem, but I'm putting that in the table anyway, just so we see it, get a little practice playing with those numbers. And if I plug in my numbers in, I get 926.6 kilowatts. All right, so I do need to calculate the isentropic efficiency. So this is W over Ws. That isentropic efficiency relates the isentropic and the non-isentropic process. So ideally for a turbine, you get a lot of work out of it, and so that's going to be the bigger number. So bigger numbers should be on the bottom, and the smaller number will be on the top. So I've got my equation for little w, that's just H1 minus H2, and then Ws is H1 minus H2. H2S. So I've got H1, H2, I just need H2S. And so now I'm on that last column of my table on the upper right-hand corner. So the two properties that I'm going to use to fix my state are the pressure and the entropy. And if I look at my saturated tables, I'll find that I'm saturated because at 0.1 bar, that S value, that 6.5282, it's between the S sub F and the S sub G value. So I know that it's two-phase, so I know that the enthalpy is defined according to that H sub F less the quality times H sub FG. So I'm ready to plug in some numbers, but I do need to get that quality X sub 2S. I'm going to use my entropy to calculate what that is because that's defined using the same kind of expression, right, that we use for calculating the enthalpy. So I know my S2S is that 6.5282 kilojoules per kilogram K. The S sub F and the S sub G values can be pulled out of your saturated tables that are organized by pressure, table A3. And if I rearrange this and I just plug in those numbers for the S2S, the SF, and the S sub G values, I get a quality of 0.78 and change. So I've updated my table up there. I've got my quality, and I can go ahead and plug in that quality to my enthalpy equation and calculate what H2S is. And if I wanted to, once again, I don't need it for this problem, but there are some other property data if I really needed. By temperature, it's still the saturation temperature. So even though we've got a different quality at state 2 versus 2S, it's still saturated at 0.1 bar, and the only temperature that it could be at and be saturated at 0.1 bar is the saturation temperature, so 45.81. And same thing with that specific volume. You can calculate it using, your V2S. It would be V sub F plus your quality, X2S, times V sub G minus V sub F. So you can calculate that as well if you needed it. But once again, I put it in gray because we don't really need it for this problem. And it's just plug and chug, and I get a quality of 78%. So if you get a quality, or I'm sorry, you get an isentropic efficiency of 78%. So if you calculate an isentropic efficiency above 78 or above 100%, you probably know you did something, funky somewhere. So yeah, probably need to check that out. All right. Well, hopefully that was helpful, and thanks for watching.